Hello there. In this lesson, we're going to look at the differences between substances and how well they dissolve, and changes to that solubility depending on conditions like temperature and pressure. So first of all, solubility refers to the maximum amount of a solute that can dissolve in a given amount of solvent. And so the standard that we usually use, or that's used often in the charts that you find online or in your textbook, is 100 grams of water. So how much can dissolve in 100 grams of water would be the solubility of that substance. When you've reached the solubility, or that maximum amount, the solution is said to be saturated. That means you are at the maximum and no more can dissolve under those conditions. And so if you add more past that point, the leftovers will just sit there in the bottom. So unsaturated solutions have less than the maximum amount dissolved in them. And so if you drop in more solute, it will eventually dissolve into the solution. When you're at the saturation point, if you add more solute, it'll make a cloudy mess at the bottom. You can stir it as much as you like, but it'll still sit there. You'll still have excess solute sitting there that won't dissolve, and so the rest of it up here, this part would be saturated. There are a couple of neat conditions where you can get supersaturated solutions. And so what that means is that there's more than should be able to dissolve at a given temperature. And we'll get to how that's possible in a second. But you can always tell the difference between the three types of solutions if you just add a crystal of solute to each. So if you add a crystal and the solution is unsaturated, well, then it'll just dissolve, right? So crystal dissolves because there's more space for solute to dissolve in that solution. If you're at the saturation point and you add your crystal, the crystal will just sink to the bottom. You can stir it as much as you want. It'll just sit there, go round and round, but it won't dissolve. If it's supersaturated, a pretty neat thing happens. The added crystal will grow, right? And more solid will be added to that crystal that you added. So that excess that was dissolved in the solution that really shouldn't be there will start to come out of solution. So we'll get to how you can end up with that condition in a minute. So the secret for making a supersaturated solution is the temperature. Most of our solids are going to become more soluble at a higher temperature, right? If we increase the temperature here, you can see the line goes up and more will be able to dissolve at a higher temperature. So if I have whatever this compound is, I dissolve at say 75 degrees, I can get 70 grams of it dissolved at 75 degrees Celsius. And then what you do to make a supersaturated solution is you cool the solution down. It's saturated at 75 degrees Celsius. But if I cool it down to say 50 degrees Celsius, now there's all this excess that's in here. So then you say that this is a supersaturated solution. So if you just took 50-degree water, you would only be able to get, say, 45 grams dissolved in there. But if you heat it up higher than that, dissolve the excess, and then cool it back down, you can end up with a supersaturated solution. Now, gas solubility also changes with temperature, only it's the opposite effect there. Since the gases aren't bonded together, there's no need for extra energy to pull those bonds apart. Gases are already free particles that are separate from each other. But as you know, if you're a fish, you definitely rely on, say, oxygen being dissolved in the water that you're swimming around in to breathe, right? And so what happens is actually the opposite effect. Warmer solutions will not be able to hold as much of those gases as a cooler solution. And the reason there is that the added energy means that it'll actually be breaking the bonds that are holding those gases in the solution. So a certain attraction between, say, some oxygen and the water will be broken if there's too much energy there. So most gases, you'll see their solubility decrease with temperature because you'd be breaking those bonds between the solute and the solvent. Pressure also plays a role in how soluble a gas will be. So you might understand that over top of us, where we're walking around here on planet Earth, there is this layer of gases that is all being pulled down towards the center of the Earth by gravity that holds all of us onto this planet. If you go up higher, say up on a mountaintop here, you're a mountain hiker or something, and that's my pickaxe for climbing the mountain here. Yeah, and so you're hiking up the mountain. There's going to be less air above you pushing down, and so the pressure is going to decrease as you go up the mountain. And so under lower pressure conditions, less of the gas will be dissolved into your bloodstream. And it'll make it a little harder for you to breathe. Oftentimes, if you're doing one of these extreme mountaineering adventures, you're going to have to take some oxygen with you in order to be able to function at those really high altitudes. Down here, we're pretty well adapted to anything at reasonable around sea level or thereabouts. We can operate no problem because we'll have a consistent amount of oxygen dissolved in our bloodstream. And then if you go diving, if you go down deep under the ocean here, if you're into the other extreme type sports, and this time those are my flippers, right? You're going down deep under the ocean and you're breathing like some air that you bring along with you. A lot more will dissolve into your bloodstream than normally would because it's under a lot more pressure as you go deeper under the ocean. This is fine for oxygen, but nitrogen is another gas that's a part of air, and if you are breathing a lot of air with nitrogen in it and it dissolves into your blood, it can take a while for that nitrogen to come out. And so if you come up too rapidly, you can get a condition called the bends, where those gases start to come out and it's really painful. So you have to come up slowly, watch your little regulator, and make sure you avoid that uncomfortable condition. Okay, so on the graph, the way all this looks then, when it comes to temperature and solubility, is that on the one side of the graph, you're going to have all the supersaturated conditions, and on the other side of the graph line, you're going to have all the unsaturated conditions. So if you're below the saturation point, then you're going to be unsaturated, and then above, then you're going to be supersaturated, more than should dissolve. So then it says, what kind of solution contains 40 grams in 100 grams of water? So this is all in 100 grams of water. So 40 grams of solute in 100 grams of water. So here's 40 grams of solute right there. At 20 degrees Celsius, there's the 40. At 45 degrees Celsius, there's the 40. And at 80 degrees Celsius, and there's the 40 there. So at 80 degrees Celsius, unsaturated. At 45 degrees, this is saturated. It's right on the line. And at 20 degrees, this would be supersaturated. So you can always tell just by using your graph. So precipitation is when a solid or solute comes out of solution, and that can be triggered if there's a chemical reaction that produces too much of a solute in the solution, or if you have a supersaturated solution and the precipitation gets triggered by, say, an added crystal or some other disturbance. So what happens is that the difference between the supersaturated point and the saturation point, that amount of solute will come out of solution and become a solid again. So with the example here, it says what mass of precipitate will form if a solution containing 40 grams of this salt is cooled to 10 degrees Celsius. So we've got 40 grams at 10 degrees Celsius. So that's the amount that's in the solution. And all of this, right down to the saturation point, will precipitate. So it goes from 40 down to about 15 there. So that's the difference then is 25 grams of precipitate. There you go. Hope that helps. Talk to you soon.